So, good morning, everybody. You still got some time to come on in and settle in as Jonathan and Albert are running around setting everything up. But I have a special guest for you today. I'd like to introduce, named Melanie. Would you like to step forward?
Hi, everyone. So I just have a quick announcement for all of you that'll only take a minute of your class. So my name is Melanie, and I'm a member of the U of T Astronomy Union. We're a course union that officially represents all students in any astronomy course or program. So if any of you are in any courses that start with AST, we're the student union that represents you guys. So if you guys ever have any questions, concerns about programs, classes, departments to do with astronomy, we would be the group that you guys reach out to. We also run a bunch of events throughout the year that are open to all U of T students, not just astronomy students. We're having one this Wednesday in the Astronomy and Astrophysics courtyard, where we're doing a meet and greet just so you guys can meet the AU execs this year, and we're gonna have Tim's there as well, so stop by if you can. Be sure to follow our Instagram, Facebook, or join our Discord server for future announcements, and thank you guys so much.
Thank you very much, Melanie. Because I need both laptops. I'm going to be going back and forth.
So you may have to, either split switch.
Okay. Just figuring out how I'm going to deal with all the laptops I've got up here. But so I've got a couple more announcements to go through. Another one is something about, it's called registered study groups. So one of my fields of research actually that I like to look into is called physics education research. There's a whole actually journal, Art of Physical Review, called the PER, in which people do studies using their students, try to make changes and see, you do pre-tests and post-tests and try to see how students learn best, how do students gain most from courses. And this is part of what you're going to be doing in practicals this week is the pre-course for this class. But one of if they look at different predictors of how much a student will gain from the course and different aspects of how they study and what their preparation is, the thing that comes up at the top of all the lists of things to do is whether or not a student joined a study group and made friends in the course. If you have kind of a group, it could be a formal one, like these registered or recognized study groups, or it could be something more informal, just finding some friends. That's kind of one of the best ways to learn, is to discuss things with your friends, because you're both kind of teaching with them and learning from them and bouncing ideas off each other. And another, announcement. This is coming from Accessibility Services. We're seeking volunteer note takers. Volunteer note taker, I guess, so they can register online if you're interested in doing that. It's another thing that. So there's a few of these kinds of things you can do at U of T which add to your co-curricular record, which is something that just goes in your transcript that lets people know who look at your transcript what kind of extracurricular things that you have been up to. And being a note taker is one of those. Although I'm posting my notes, so, you know. Also, thank you so much for doing the pre-class quiz, either on the weekend or this morning. It was due at 9 o'clock, I think. I looked through some of your comments. I have to actually figure out a way to get it to post your mark out of 3, because the comments and that question about your friend, those were worth 0 points. So it really is just out of the 3 points for the multiple choice questions. But apparently I have to go through and press 0 out of 0 for all of them before it'll display. So I'm working on that issue. There's an announcement about this. I've never understood why significant digits are important. Can you please explain how they affect anything? That's a really good comment from a student, because I've puzzled about this myself. And in fact, among the professors in the department, there is a sort of a bit of a debate, and there's sort of half of us that fall on the side of, it's a little overemphasized, what the hell is the point? And the other half, I think, is really, really important. And so I could kind of play a little bit devil's advocate and let you know what some of my friends think about significant digits. Is that basically their idea is that if you say that something is equal to like 1.312567, but really you only know that it's somewhere between about 1.30 and 1.32, then you're kind of lying by specifying all those digits, because it implies to the reader that you have an uncertainty which is very, very small, a very high precision measurement. Now, really, the solution to this is to just write down your uncertainties. And when you're in a lab, like when I was in a lab, or when I am in a lab, I just write down everything that comes up on my calculator, because that's how I roll. I don't like to round things. And I just write the plus or minus on it as well, is what I think the uncertainty is. And it doesn't matter how many. But I guess if you just are going to write the number, then if you write 1.3, there's sort of a hidden implication there that the uncertainty is somewhere around 0.05. But if you were to write 1.3001, then there's a hidden uncertainty there that implies it's much more precise. Like, where did the 0.001 come from, right? I don't know. But I think, and what is definitely true is that every first-year physics textbook I have ever seen goes into great lengths to promote the significant figures things and significant digits. And so it's important to somebody, that's for sure. Oh, and then there was something about adding. If you add 30.58 plus 0.3, the question is, how do you round off the 30.88 that you're going to get? Should you just use one significant digit or what? So the rule for multiplication and division is that you would just use if you're like multiplying by 0.3, then that's one significant digit. You just round it to, I guess, 31 or something, or sorry, 30. But when you're adding or subtracting, the rule is you keep track of that like tens column. That's the least accurate. So in this case, the 0.3 is specified to the tenths column, so you're supposed to round the final answer to the tenths column. I'll talk a little bit more about that today. Do we need to memorize the SI units or just be comfortable? So you don't have to memorize anything in this course because you get an aid sheet, right? So that's kind of nice. If there is numerical information or unit conversions that you need, I always put those on the first page of every test, just so that you don't have to write down the numbers on your aid sheet. The aid sheet is mostly for the equations that you don't feel like memorizing, or any little helpful tips or example problems or whatever you want. Motion diagrams. So motion diagrams don't come up that often in an actual test. For example, this first mini test that you have on September 26th will all be multiple choice. And so you don't have to draw motion diagrams for that unless you want to, as kind of as a way to help you understanding what's going on. But when you get to tests, the real test one on October 10th, there will be a written question, and one of the 4 steps that I'll be talking about is called the simplifying diagram step, and it might be appropriate to put a motion diagram there, so you might be asked to do that. And yeah, is the test going to cover just stuff in the class or also the textbook? So it's the textbook is really, so this is the textbook. You got to get that. I only have 50 minutes, to talk about it, not including all the questions that you're going to be doing and discussions. So I'm not going to be covering everything in class. I'm just going to be kind of hitting on the high points. So chapter 1 through 11 of the book is what you're expected to know for this course. So thank you so much for all of those comments. It's really cool to hear from you directly. Is this thing working now? Or, okay. We don't need it right now, but we do have a microphone if you guys have questions. So let's get into chapter 1 and kind of go over it again. We sort of did talk a little bit about what physicists do, collecting and analyzing experimental data, making explanations, testing them, creating different representations and models, and testing these hypotheses with new experiments. So it's kind of what me and my friends do over in the physics department. And one of these is this, the point-like object. So let's approximate this as a point. So this would be sort of a real-life kind of photo of an object, a race car. But what this is the point-like particle model. Because really, point-like particle model. the things that we often care about, we don't maybe in a physics problem care if it's the blue car or the red car or what decals are on it or even that there's a human being in there or what the blood pressure of that human being is. We're trying to get rid of all the extraneous data and come down to what do we really care about. And in fact, we don't even care about the shape of the car or that it has 4 wheels. What we care about often is who's going to win. And so that means where is the car and what's its velocity? How fast is it going and in what direction? And you can specify all of that information by, I guess, approximating the car as a point. And there's that old joke, which I don't know if I'm going to tell it all that well, about, I guess, a conference for farmers, and they have these guest speakers that come in. They're going to talk about how to raise cattle or something like that. And of course, there's a veterinarian who gets up and talks about, oh, well, the cow has 2 stomachs and all this. And then the next person that comes up is, a biologist and says, talks a little bit about animals and plants and animals and how they relate in their environment. And then a physicist is the third speaker, and the physicist says, first, let's model the cow as a point-like object. Okay. So, didn't go too well. I appreciate it. They're called dad jokes for a reason. Okay, so next, I have this question, and I'm going to start it pretty soon. There's a join code, which I don't know if you need it, but it's something called Top Hat. You need like a phone or a laptop or something right now, or you can even, I think, use an SMS message to a phone number. I'm not sure how that's going to work, though. Should I start it? I'll get it kind of going here. There will be a phone number I'll show on the board pretty soon. But one way of doing this is you go onto Quarkus, this Quarkus page, and click on the Top Hat link there, and that should take you directly to this course. And then you'll see that there is a class in session right now called Class 2, and you should be able to get in that and start to see a question, which I'm about to display on the board. If you're brand new to Top Hat, there's this sort of one-time process you have to go through to create an account, and it's like $36 or something, $38 for the year. I am new to the Top Hat system. I do like discussion questions, and I've used various systems over the years, but I've heard good things about Top Hat, particularly from Professor Anya Harlick, who's teaching the Physics 132. She was using it in Calgary and says it's great, so we'll try it out. Okay, and the way I'm scoring this is that every question is a point, I guess, and you get 0.8 just for answering it, and then an extra 0.2 for accuracy. So try to, and you only get one chance, so hopefully try to wait before you answer. And also, we're going to do this like 35 times this semester, but the lowest 3 scores will be dropped from that calculation. So if you miss a class or do really poorly in the class or something, I'll just take the top, I guess, 32 out of 35. Okay. So this is the question, which is that, without looking it up, what do you think? So these are different, what are called orders of magnitude. So every answer here is different by a factor of 10 at least. And so you know about water, you know about kilograms, and you know what a meter is, and a meter cubed, I guess. What do you think roughly would be the density of water? And so feel free to discuss with your neighbor before you click in. Hopefully you can see this. Oh, submission's closed. That's not good. I think it timed out. I want to launch it again.
I'm here to help if you need. Not familiar with Top Hat?
Yeah, me neither.
Here it is.
Okay, so I guess we're doing it twice. I've launched it again, and what I don't want is the timer. I guess I can just add more seconds. Let's give you another minute and 30 to try answering that again.
My all is set up. That's good to go.
Okay.
Next time I will bring the switch. So
A
next time I'll bring
switch for the, yeah, I remember
HDMI.
Pius needed that now because there's not quite enough inputs.
Right. So if just for this lecture it's
Yep.
okay, here's the, I can do this, it's no problem, but here's the camera.
Okay.
So whichever you feel we
Yeah, I can
feel-
unplug this one.
Yep,
Yeah,
okay,
okay,
that can
that's a
work.
good idea.
And then I tried setting up this can for this thing, but I think,
Just use the.
yeah, it keeps getting blocked. It's very funky. It keeps getting away with the camera, so I'm gonna play it. And then, yeah, on the way to the demonstration, I'm gonna adjust where the camera is pointing to as well. So everything should be good.
Okay. Yes. The other option, I suppose, is that after this class, what I will do is open it up for the online section, and then you can do it that way as well. So I kind of prefer you to do the questions in class if you can. That way you're discussing this stuff. Did you have a question over there? Okay, so that's a good question. Someone just asked about the Piazza. The idea of Piazza is that it's an optional discussion board where you can post questions and get quick answers from other students, but it's not at all part of the Top Hat system. I was thinking that there was a discussion board on Top Hat. Is this done? Want to see what the answers were? I'm not used to this automatic timeout, but most people are clicking on 1,000 kilograms per meter, which is actually what I like as well. And the idea is that this is sort of an estimate. If you think about a 1 cubic meter bathtub, which would be 1 meter by 1 meter by 1 meter, filled with water, it's not going to be 1 kilogram of water. It's going to be a lot, maybe even hundreds. And so I think that probably, and it is 1,000, as it turns out. I think that 1 kilogram of water is like 10 centimeters by 10 centimeters by 10 centimeters. And then so there's 1,000 of those actually in a big cubic block. So this just a way of kind of doing a sanity check. I think the 1 is also if you use units of grams per cc. So that's different, right? I think a gram is a thousandth, and then a centimeter is a hundredth of a meter, and somehow there's a 1,000 there. Okay. So density is the amount of mass per unit volume of a material, mass divided by volume. Unit of density is either kilograms per meter cubed or grams per centimeter cubed. So there's a way of kind of converting that out. Whoop. Either 1,000 or 1, depending on the units. So it is important to specify units. All right, and I did promise you I'd talk a little more about significant digits, so let's do that for a bit. The number of significant digits is the number of reliably known digits in a number. And it's usually possible to tell the number of significant digits by the way that you write the number. So for example, 23.21 centimeters has, let's count them out here, 1, 2, 3, 4. 4 significant digits. 0.062 only has 2 significant digits. So one way that I would try to remember that, so if you write it in scientific notation, it would look like this: 6.2 times 10 to the minus 2 centimeters. So this number is the same as this number, and then I think it's much more clear when you look at the scientific notation to see that there's 2 significant digits there. The question when you look at it just written out as 0.062 is, are the zeros significant or not? And then what I think to myself is, did the person have any choice in writing the zeros? If there's no choice, you had to write the zeros, then they're not significant. Okay, because it doesn't mean that you measured them, you're just giving placeholder. So you had to write the 0. If you didn't write those zeros, it would be 62, and you'd be talking about something else, right? So I was forced to write those zeros, so they might not be significant. Make sense? So then 80, I think, to me, this is either 1 or 2. It's kind of ambiguous. If someone says 80 kilometers, it could mean plus or minus 5, like somewhere between 75 and 85. It could mean plus or minus 0.5. They really mean 80, and they don't mean 81. So I don't know what that is. I think it's probably 1 to be on the safe side. But if they write 80.0, then think about this. That last 0, they had a choice whether or not to write that 0. No one has to write 0.0 to talk about 80, right? So now, all of a sudden, all these things become significant. I've got 3. 3. Okay. Okay, when multiplying or dividing numbers, the result has as many significant digits as the number used in the calculation with the fewest significant digits. Example, if you do 11.3 times 6.8, if I just type that into my calculator, I get 76.84, which is correct. But if you're worried about losing marks for significant figures or significant digits, you should round it to the nearest, like to 2 significant digits. So we're actually telling you to round it off, which again, to me is a little strange because you're introducing rounding error when you do this, but it's the rule. And so 76.84, you want to round it to 2 significant digits because of the 6.8. And you get, it rounds up, I guess, to 77. So it's to a lot of people, it's more correct to write 77 than it is to write 76.84. Maybe one of Yeah, what if it's 0.0080? So, what do you guys think? How many? 2. So, okay, so these are, not significant, these are placeholders. This one is significant, so sig, and this one is sig. And these ones are not. Does that sort of help? I guess so. Yeah, well, but I mean, if it was 801 as opposed to 800, this has 1, and this one has 3, because now this is sort of in the middle. The middle zeros are always significant, I guess, right? If they have non-zeros on the other side of them. It's kind of weird. I'm sorry about all this stuff. And you know what we should do, if there's other questions, is we could try out using this mic ball so that everyone can hear you. But, so do you want to try it? Do you want to feel like trying my one? I'm going to throw it. You ready? Good catch.
All right. Oh, it's working. So testing.
It's not working. Okay.
Hello.
I only have that microphone on.
Maybe it's. What if I hold it further?
Okay, maybe we'll try this a little later. We got to work on this one. So, it's supposed to be so that's supposed to be the tossable microphone. Again, we're working on this. What is your question? I sure wish we had your microphone. I should have given you maybe another. Maybe we could use that, the roaming microphone. Because I agree with everything you just said. So if I can paraphrase, these significant digits, if you're going to round something, you should only worry about, first of all, that it's a written question. Second of all, that it's the very last thing you do. So I tend to keep around 5 or 6 significant digits in all my intermediate calculations so that I'm not introducing some rounding error in my intermediate calculations. Because if you keep rounding, you're going to get the wrong answer at the end. So don't round until the very end, and then round. It's just for a display issue, so that you're not losing marks for significant digits. So.
Test it quickly.
Yeah, sure. Let's test that one. No.
Gotta do this guy.
All right. Jonathan's going to work on that. Okay. Let me give you some more examples. When adding or subtracting, the number is no more accurate than the least accurate number used. We're almost done with this stuff. Let's actually do another top hat question. So all of these answers are actually the same. This one doesn't have a timer. But they are rounded to a different number of digits, significant digits. So maybe just pick one. And please just check with your neighbor. We'll give you, let's give you 60 seconds. Check with your neighbor.
I'm not quite sure what that was, if it was coming off of your mic or somewhere in the room, but maybe I'll talk to you.
It wasn't my mic because I turned mine off.
And I turned off every mic
Yeah.
except this one, so I'm
It's
not...
that one, I guess.
Yeah, maybe it's feedback off itself. But that mic works.
Okay,
I
okay.
built that. And I have it turned on from the volume thing here, but I have it turned off this. So if you like, if there is someone who has a question, and they're in the bowl here, I can run the mic to them, no problem.
Okay, awesome.
Yep.
Good.
So far so good, I think.
Okay, 10 seconds to try to click that into your top hat. Get this done. Okay, so let's see what it does here if I do responses. So, and I think that's right. And I wonder if I can, yeah, and it lights it up green if I do it again. So that means that that's the one that I thought. So going back to laptop 1, reason being that this has 4, this has 3, you use the least, and then you round to 3. So that's the idea there. Okay. And I wanted to do a quick sort of example. Scientific notation is often used. So for example, if you write down 36,900, it's hard to know how many significant digits that is, but however, every time you write it in in scientific notation, it's much easier to count. You just forget about the magnitude is specified by the times 10 to the something, and then the number ahead of it, you just count the digits, and all the zeros and everything are counted. So that's sort of, if you're getting confused, write it out in scientific notation, and then you can't go wrong. So let's do a quick example where this might come up. So my daughter's just turned 12. I really got to get a new photo. But so this, if you look a little closer, what it says there is no smoking within 9 meters or 29.5 feet of the playground. So which is it? And how many significant digits did you... So I got a little curious about this one day while I'm pushing my daughter in the swing or something. And I looked up the bylaw, this City of Toronto bylaw, and it actually does say 9. They spell it out there. And so I think City Council intended only one significant digit. So if you were to do this in a physics class, first of all, these are like the unit conversions that you were given on the test. If you put the D is equal to 9 meters, one way of converting that is to multiply by things that equal 1. So 1 equals all this stuff. So if I want to convert meters to feet, I want to get feet at the end. So I'm going to multiply. I think there's 3 numbers I can multiply. I want feet. So the foot, the only thing that has foots in this is that there's 1 foot in 12 inches. So then, if I write inches up here, then the inches will cancel. If you see what I'm doing here. I want inches to cancel with inches. So now I can write like, I need a thing with inches on it. I know that 1 inches equals 2.54 centimeters. So I need something with, my goodness gracious. I leaned on it. Be careful. I need centimeters up here so that the centimeters will cancel. Centimeters cancel with centimeters. So what's the conversion that has centimeters and then meters, right? So I know that there's 100 centimeters is 1 meter. So that now the meters cancel. So what I need to do to convert these units is I'm going to say it's equal to 9. I'm going to times it by all the things on the numerator and divide it by all the things on the denominator. So I'm going to do times 100 and then divided by 2.54 times 12. So that's just a handy way of converting. And I ended up with 30 feet. Probably the 29.5, but 30 feet. Or better, 3 times 10 to the 1 feet. That really shows that there's only one significant digit. But who would say 3 times 10 to the 1? But, okay. Another thing I want to talk about quickly is this, what's called the problem-solving strategy. And this is a big deal in Chapter 2 if you've been reading it. So let me go through it a little bit. It's 4 steps that when we get to this test on October 10th, I'd kind of like you to be able to show how it works. So the first step is try to draw a diagram, or a sketch of the situation, I guess. Write down what your knowns and unknowns are. Second step is to try to neglect some of the irrelevant details and maybe do some more diagrams, and maybe a motion diagram is appropriate here. So that's a bit different than a sketch. A sketch might show just what physically is happening, and a diagram might be like, what are the forces on an object or something. And then you're going to set up your equations and maybe solve symbolically for what you want to do. And then the very last step is to plug in the numbers and then kind of, again, do one of these, like think about your answer. Same way we might have thought about 1 kilogram per meter cubed. What would that look like? Like a sanity check kind of thing. Does this make any sense? If you get that the height of the CN Tower is 10 to the minus 6 meters or something, you may want to scratch your head and say, oh, I wonder if I did something wrong there. It's clearly not right. Okay. Good. So we're getting into Chapter 2 stuff. Motion is a change in an object's position relative to a given observer during a certain change of time. So if you don't identify an observer, you can't say what the velocity of something is. So another way of putting this is that motion is relative. And so the joke there is that you ask the physicist, why did the chicken cross the road? And then the answer is, well, wait, did the chicken cross the road, or did the road just pass underneath the chicken, and the chicken is the center of the universe? As you can think of, again, no need for clapping at dad jokes, really. But idea being is that everyone's at rest in their own reference frame. And so even if you're driving along the highway at 100 kilometers per hour, another equivalent way in physics of looking at that is that you're at rest, and all the trees and buildings and everything are rushing by you the opposite direction at 100 kilometers per hour. And if you've ever noticed, if you were to take a beanbag in your car and kind of throw it up and down, you're in the back seat, it feels like you're at rest. It's not like the beanbag goes flying off, right? So that sort of is a way of proving that it doesn't matter. What matters about your velocity is the reference frame. And it's certainly going to be important if there's a building in front of you that slams into you, but motion is relative. That's what relativity means. Motion diagrams. We're going to talk a little bit about that. I'm going to try to kind of do it, but if you imagine an old kind of movie, which movies used to be these actual frames on I guess, cellophane or something. If you were to, and what a movie does, or a video, is it takes many images per second. So each photo is called a frame, and if something's moving, then it's in a different position in the different pictures. Whereas if something's stationary, then like the tree, it's in the same position. So if you were to take all those pictures and kind of stack them up on top of each other, you get kind of a strobe image like this. And that's what a motion diagram is. And sometimes you can replace the object with the point-like model. So, Jonathan, can you help me switch over to the... We'll see if we can do this demo. So what I'm going to do is make my own motion diagram using the penguin. Let's see if we can zoom in on me here. We're working on an HDMI switch. So now laptop 2, I think. This way you guys can see me a little better. Hello. And you got to see my penguin too. So again, what I recognize partly is I can barely see some of you up in that balcony. Hello, balcony people. So it means you can barely see me, right? So, but here I am, and here's my penguin guy. And what I have is all these bean bags, so I'm going to turn them on. And then what I'm going to do is try to make a motion diagram by kind of dropping bean bags at the ticks. Make sense? So something's going slow, so let me get into the groove. Tick, 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 tick. Okay, not too good. But you can see a couple of things. It was going slowly because the bean bags are all sort of close to each other. And it was slowing down a little bit because of friction. If I was to speed it up, maybe launch a little faster, get into the groove. Okay, going a little faster. Now the bean bags are more spread apart because in between ticks of the penguin, it goes farther. And the distance divided by the time is the velocity, so if it's going faster. So then the other fun thing we can do, you get off is use the physics textbook and prop it up and get a little bit of acceleration going. So that's fun. We need a longer table too. But what if it starts like at rest? Okay. You got it? So they get kind of farther apart. Well, it doesn't look that great, but if the beanbags are getting farther apart for the equally spaced metronome ticks, then it's speeding up. So that's motion diagram. So thank you. Okay. Awesome. And now we need a top hat question. And it is luckily gone blank. Oh, here we go. Good. Next. I think I'm pretty good. There we go. It's working. We'll do 2. And please discuss with your neighbor. You got a minute? Make sure you know which one it is. Because it is. You get the full point if you get it correct. And you only get 0.8 if you get it wrong. So.
Curious about. Yeah, it's way too loud. That was the issue. It was at maximum volume. Okay, let's turn it all the way down. Okay. Do we dare? I think
could be ready with the mute button.
Okay, I think we dare. Okay.
Okay. Okay. Want to do another one? So for that one, most people got it. I'd like to see percentages. So, there we go. And then, so 93% of you got B, which I like. They're farther apart, so they're going faster. Let's do one quick more one. Oh, you can barely see it. I don't know if you can see it on your phones a little better. Let's look at, I'll just show you on the laptop quickly, or on the screen quickly, that is it, which of the two objects is speeding up, A or B? C would be, oh. Same speed. That doesn't look right. And then D is cannot tell. So this is kind of wrong. Same speed. I don't know what that means exactly since they're changing speed, but there you go. I think I messed up this one a little bit. But there is an answer I'm looking for. So I'll give you 60 seconds, and then I'll discuss that one. Okay.
This is a test. This is a test. 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 This is a test.
Yeah, that's a good point. Yeah, for the last question, there was an assumption there that they both had the same amount of time between dots. And it's the same for this one. Yeah, that's a really good point. I should have stated that assumption. That's one of the things this textbook is very careful about, and maybe I'm not as careful as I should be, is stating your assumptions. And so there was this unstated assumption, which I should have stated last time, was that for both motion diagrams A and B, it's the same amount of time between dots. So for this one, what I was looking for, see if this works here. Yeah, was cannot tell, because you don't know which way they're going. There's no numbers on it, right? So, sorry about that. That's a little evil. But, so basically, thing being neither, we don't know which direction this object is going. It could be going from left to right or from right to left. Which direction? And the way that it's good to resolve it is you can just put numbers on the motion diagram. So if it goes 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, then you're right. Then this is slowing down. And then this is speeding up. B would have been right. But since I didn't have the numbers, then it's hard to tell, right? Okay, now what time is it? I guess the last thing I want to talk about is, because I guess, we'll just do it really quickly, maybe you can agree with me. What if I did this? Pen. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. If both of these objects are moving towards the left, then this one is speeding up. And this one is slowing down. make sense? Sorry about screwing you guys up there. Okay. So just quickly at the end, what I want to talk about, we're getting about 10 minutes left, is these position. So this is velocity vectors. So then I'll talk about position time graphs. So velocity vectors are when you connect, I guess one way of putting them is to connect the two dots in adjacent dots in a motion diagram, meaning that you've got an arrow, first of all, that starts where in an initial position and then goes towards a subsequent position. And the length of that arrow is related somehow to the speed of the object. And the direction of the arrow is which way it's going. So that's velocity. So you can see if there's a hare racing a tortoise, which means a rabbit racing a turtle, then the velocity vectors are longer for the hare because it's going faster. And then lastly, I want to talk about position versus time graphs. So if I take a ball and I move it slowly over some amount of time, maybe 10 seconds, from a 0 on a ruler to 20 seconds on a ruler, then there's sort of this question of how can we represent that motion. And you could do a motion diagram, I guess, and get a bunch of dots. But another way you could represent the motion is to make a table of position in one column and time in another column, or I guess time first and then position. So you're reading time off a stopwatch, for example, in seconds, and then you're measuring position on the ruler. And so for each second of time, you could list that position. You could just read it off. And you get all these pairs of numbers. And so if you have a bunch of pairs of numbers, then there is this, we all sort of feel it, right? There's an urge to graph it. Like, that's what I feel. I see a bunch of pairs of numbers. Hey, what would this look like on a graph if I were to take, like, all the things in the left column and put it on the x-axis, and all the things in the right column and put it on the y-axis? Make sense? And you can graph all those numbers, and you're going to get a diagonal line. And if I do it, it looks like this, in fact. So this is what's called a position time graph. It's very, very useful in physics. It's going to be super important once we get to like acceleration and things. But it's a bit abstract because these have totally different units. You're not really drawing anything real, right? You've got time down here, read off a stopwatch, versus position, which could even be x on the vertical axis. So this is what we do. We draw this concept of time on this axis, position on this axis. Then we can even do something a little more subtle and connect the dots to make a sort of a trend line. And now we even have this sort of assumption that if something was at 0, 0, and then went to position 2 centimeters at 1 second, then for every instant of time in between there, we can infer that it was at, all these different little, every position was visited by this object. Sort of subtle, but we only measure it, but we assume that it moves kind of slowly through space. And we can do all kinds of things with the position versus time graph. We can measure the slope. So if you do rise over run, think of it this way. The rise will have units of centimeters, and the run will have units of seconds. So if you were to divide rise over run, you get centimeters divided by seconds, centimeters per second. That's a velocity unit. So the slope of this graph gives you that velocity. So again, super, super useful. Don't forget to go to your practical section this week. Some people might even have it this afternoon. You either go to room 122, MP 122 or MP 123. It's back in the physics building. If you don't know which of those two rooms, they're right beside each other, so you could just ask around. April has also posted a list of names on a glass thing right across from room 122. You should see your name there, and then you'll know which room to go to. You can also go to groups on Quarkus and probably figure it out as well. Whoop. And this week, it's just the pre-class survey and quiz, which should take no more than 50 minutes. And somebody asked me outside in the hallway just now, is it for completion or for accuracy? And the answer is, you get full marks for completion. But I hope that we're going to be learning this stuff this semester, so please try your best if you can to answer as well as you can. And between now and Wednesday, please take a look at the pre-class quiz and something to think about. Does constant velocity imply constant acceleration? And does constant acceleration imply constant velocity? Do you know the answer? Something else?